Swayam Prabha. Digital India. Educated India.
Welcome back. In the last lecture, we started a discussion on the traffic management, and we looked at one of the service model called as the integrated service model. Today, we will discuss about another service model called as the differentiated service model. And here is the agenda, what we will be discussing in this lecture. So, we will look into the motivation for the differentiated service, where exactly the integrated service actually lacks, and we'll also look into something called as the code points and the per hop behavior. So this is the agenda for today's lecture. So the differentiated service model originated because of the inefficiencies of the integrated service model. What the integrated service model offered you is a kind of the service which is making a reservation of the resources all along the path. So meaning if the source and destination want to engage in conversation, or two endpoints want to engage in the conversation, so the first is there is a signaling protocol called RSVP that runs and makes a reservation all along the path at every router. And this reservation actually puts a lot of pressure on the intermediate routers. So they need to remember which endpoints require what kind of the bandwidth and other things. And by virtue of that, remembering that itself, and then at the runtime, and comparing them would be a challenge. So what the differentiated service model brings you is, it simplifies the reservation model. There is nothing called as the reservation. What it does is, it identifies a set of classes of the service model and maps any application requirements into one of these available service models. And then the traffic actually flows following that the nomenclature. And what it also does is, by simplifying that, it also puts a lot of the whatever the marking need to be done that at the endpoints. So much of the complexity is at the points. So let's take an example. So let's say this is the network, and the end user is somewhere here. This is the computer which connects to this network via this link, and there is a router here. And this router, we called it as the, remember, this is not the router at the boundary of the network, somewhere which is where the end user's computer is connecting, called as the edge router. So edge routers or the service routers provides services to the end users. And there are a bunch of intermediate routers in this network through which the packet actually flows, and it reaches something called as the border router and then enters into another network's territory. And what the differentiated service tells you is, once the packet arrives at the edge router, let's call this packet as the P1. When it arrives at the edge router, you mark appropriately this packet, meaning I am going, depending upon the what type of the content is actually going through this packet, or what application actually has sent it, or which customer has sent it. Based on that, I am going to put something called as the code point, or some marking is done to this packet, using which the rest of the routers within this network are going to just look at that code information or the marking that is done, and then forward the packets. So forward the packet with the appropriate priority, and the when to drop, differentiating when to drop which packet, looking at the code. That's what the differentiated service is all about. There are only handful number of the such code points that the differentiated service defines, but using that the actually routing or the prioritized service or the quality of service is actually provided to the network services. And the way it operates is, the differentiated service model operates is, it defines a set of the service level agreements to the end users. So the service level agreement might say that I'm going to provide you, the network service provider might tell you that I'm going to forward your packet with a certain priority with so much of the fraction of the total traffic that I receive, maybe 99% of the traffic that you send to me, I am going to forward it to the correct destination within this timeline. That's what the service level agreement look like. And in order to realize this service level agreement, there are certain rules defined. So that is called as the set of the rules is called as the traffic conditioning. So that's an agreement between the end user and the service provider. So that's how the differentiated service actually operates. So we look into the details of how this code points and other the differentiation actually look like, how the marking is done. So before that, let's look at the IP version 4 header and then carefully examine where exactly this marking is actually put. So here is a picture of the IP version 4 header, and there is one field of interest to us which is called as the type of service. And often you might have seen that this field is sometimes marked as the type of service field and sometimes marked as the differentiated service. Here it is, DS stands for differentiated service. So this is the same 8-bit 1 or 1 octet field from the bit number 8 to 15. So this field is sometimes referred to as the type of service and sometimes it is as the differentiated service. So differentiated service is the one which is in our context what we are going to be discussing. But this has differentiated service has a history. The reason why this is marked as a type of service is before differentiated service actually came into picture. Earlier, the standard was talking about something called as the type of service. So that's why sometimes you see the IP version 4 header being marked as type of service and sometimes as the differentiated service, this particular 1 byte data. So this type of service, earlier I said that differentiated service model came later, and prior to that there was something called a type of service. So type of service standard was defined to provide something called as the precedence. That precedence is called as the IP precedence. Precisely in the year 1981, RFC number 791 actually defined this standard, providing some kind of the differentiated service or some kind of the quality of service to the different packets. So the type of service field, 1 byte, was divided into 3 parts, to be precise 2 parts. First 3 bits from the bit number 0 to 2, 0, 1 and 2, define something called as the IP precedence that indicates when to drop the packet, which packet need to be dropped, if at all a router has to drop a packet. And the remaining 5 bits are supposed to be indicating something called as the type of service field. And out of these 5 fields, 2 bits are reserved for the future use as of the RFCs in the 791. So this was not defined. But the other 3 bits, bit number precisely 3, 4 and 5, were indicating 3 different quality of service parameters called as the D stands for delay, T stands for throughput and R stands for reliability. You can ask, I want so and so delay, I want so and so throughput, I want so and so reliability from the network, and the network will try to provide that kind of the service to you. So these 8 bits divided into 3 parts. The first 3 bits as IP preference and the next 3 bits indicating delay and throughput and reliability, and the next 2 bits are actually reserved for the future use as per the RFC 791. And as we can actually check, IP precedence being the 3-bit field, so there are 8 different values that IP can take from all zeros to all 1, and the first column here indicates the decimal values corresponding to these 8 numbers from 0 to 7, and the name given to these are the all 3 bits set to 0 indicates the routine topic. That's the, you don't do any differentiation. The best effort IP service model, using that you forward the packet, and the next priority level is indicated with the 001. And if the first 3 bits within that 8 bits are set as 001, then you need to give some level of the priority. And if the number is either 010 or 011, something like that, then the priority level keep increasing from this being the best effort service model, the routine. So this is the default service model, and from here to here as you go, the priority level actually increases. So meaning, if at all you have to drop a packet, you need to drop a packet with the lower priority, so preserving the higher priority packets in the queue. So that's how this IP precedence is actually defined. And this is a story about the first 3 bits, and the next 3 bits, as I said, indicate the delay, throughput and reliability. So these 3 bits are independently defined, meaning when the bit number 3 is set to 0, it indicates that you are not expecting, or you are not telling the router or the network to provide any kind of the load delay. Whatever the default delay with which the packet can be transmitted, you just transmit with that. If it is set to 1, then you are telling the network or the router that this packet need to be forwarded with the low delay. And similarly, bit 4 and 5 are also, if they are 0, then bit 4 is 0, then it indicates the normal throughput. If it is 1, that you are expecting a high throughput. So bit 5, similarly, if it is 0, it is a normal reliability, and if you want a higher reliability, you set it to 1. So as you can see, what is shown in this table is the possible combination of the values that you can specify. So by appropriately setting a delay or throughput or reliability component to either 0 or 1. So, but often although this is possible to us, the RFC 791 mandated that you don't put or ask more than 2 of these parameters in one go. Meaning, so if I want, the best possible case is you want a very low delay, very high throughput and very high reliability. Often these requirements are very hard to meet. So some of them are conflicting with each other. So in that sense, so putting all these fields and asking for all these parameters to be met in one go actually complicates, which the network may not be able to meet those requirements. So what it advocated is, at max you set 2 of them. Either you ask for the low delay, or you ask for the low throughput, and not the other one, or any 2 of them. So in that sense, you are actually not asking too much from the network. So back then in 1981 and subsequently, the network was not as we see today. The bandwidth was a very scarce resource. So meeting these quality of service requirements or the expectations would be very hard in those days. That's why it's actually asked to limit to only 2 of them. And that's the story. That's the beginning of the first case when the some kind of the quality of service notion was brought into computer networks. Subsequently, RFC 1349, approximately 10 years later, it came and modified this type of service field. So the division still looked the same. You use the 3 bits for the IP precedence and the another 5 bits for the type of service field. But in the previous case, you were using 3 bits for delay, reliability and throughput. Now it says that a combination of the 4 bits should be used to indicate different kinds of the type of service. And it reserved only 1 bit for the subsequent or the future case. So the changes made in the RFC 1349 look something like this. The IP precedence values still remain the same thing. There are no changes in those 8 values that the first 3 bits define. But what is changed is using the next 4-bit combinations, you define different service classes. So, for example, 1000 indicates you require a minimum delay from the network. That's the expectation. So 0100 indicates you need to maximize the throughput and so forth. So 0010 indicate maximum reliability. 0001 indicates you consider some of the type cost parameter into account. I want to send this packet with the minimum overhead or minimum cost from source to destination. That's the meaning of 0001. And all zero set for all the 4 bits indicate the default service, which is the best effort service model that the IP offers you. So that's how the changes were made to the IP precedence field. So, but although this actually defined a notion of the quality of service in the IP model, IP service model, but it never really took into the real networks. None of the practical network service providers actually used this IP precedent model or the type of service model into their network and implemented and provided the differentiated service. So it's more of a theoretical exercise than the real implementation in the real network. So subsequent to the 1991, where the RFC 1349 actually into picture, so people found that this service model, the IP type of service model, is also inadequate. So it doesn't provide the kind of the differentiated services that I want in the network. So that's where the differentiated service actually came into picture. So these people started talking about how do we actually provide the differentiated service over the best effort IP delivery service model. So what people started talking about is the network service providers started talking about providing the service level agreements to the end users. Meaning, as I was referring to in the first slide, the network service providers will come and tell you, I'm going to give you so and so amount of the bandwidth, and this bandwidth I'm going to commit to you for 99% of the time, and the maximum downtime that I would experience would be less than 1% or 0.5% of the total time duration, and I'm going to give you end-to-end delay of so and so, something like this. So the service providers started engaging the customers by formally defining the service level agreements. So meaning, so by specifying all of them, the service level agreements are also specified something called as the penalties. If I don't meet these requirements, what is specified inside the service level agreement, what kind of the penalties that the service provider is going to take. So if there is some issue with the service that they provided, then whom to contact. So if there is an issue, then how exactly they resolve that issue, and what is the escalation matter if the first person who is the point of contact is not able to resolve the issue, whom to contact, and how the escalation matrix actually works. So all these details were actually put into this service level agreement. And so this service level agreement is more of a non-technical specification, and in order to realize these non-technical requirements into reality, there is something called as the traffic conditioning that is defined. So traffic conditioning is, so I am going to give you this kind of service model, this kind of the service, and in order to realize that service level agreements, so the end user traffic need to be conforming to something called as the profile. So for example, if you transmit less than 1 Gbps of the data, then only these service level agreements are going to be met. As long as the traffic rate or the peak rate is less than 1 Gbps, I am going to give you a bandwidth of so and so, I am going to give you an end-to-end delay of this much and so forth. So if you violate that 1 Gbps, that's the profile. 1 Gbps, then there are consequences. The end user, the service provider is not going to guarantee you that the same kind of the reliability, same kind of the end-to-end delay for that kind of the traffic. So that's what the traffic conditioning agreement is. So you define what is the traffic profile. So if the end user traffic profile is meeting what is defined in that profile, then the service level agreement are going to be in force, and then you can actually expect that kind of the service from the service provider. So using that model of the service level agreement, the differentiated service actually took up from the pace. The real implementations actually came into the service provider networks. So the service provider, the differentiated service actually defined a kind of a framework or a kind of the building block with which you can actually realize this kind of the differentiated service or the quality of service in the internet. So it actually provided a kind of the configurable parameters using which the traffic from the different applications and different users are treated differently. So as I said, much of this complexity is placed at the edge router or the first hop router, where the packet marking is done, and then subsequently in the network the packets are the routers are looking at that particular marking and then doing the forwarding differentiation, meeting the quality of service requirement of that particular packet. So what can often happen is, although this is defined at the first hop router, what can happen is this is the first hop router, and then as I said, there are a bunch of intermediate routers, and then you go to the next level of the network. So from one network to the another network, when the packet transit, when I say this, the edge router, the marking is done. That marking is actually valid only in this particular network. So for example, it is possible that the kind of the quality of service, the way it interprets the quality of service in this network is different than the way this service provider or the network actually interprets. So there might be, so for example, hypothetically, there are 10 different classes of the quality of service type of the service, but here there may not be 10, there might be only 7 of them. So I need to find a mapping of these 10 quality of service parameters, or the what we call it in the differentiated service model as the code points, to the mapping to the these 7 of them. Which one of this one maps to which one of the different type of the code point that we have in the second model. So by virtue of what I want to say is, so when the marking is done, that marking is valid in this particular network. When it hits the boundary of this network and entering into the another network, the same packet might be remarked at the edge router or the boundary router of the second network. So here the marking might be changed. Marking is changed or not necessarily changed. If it is if the marking is same in the first network and the second network, then the no remarking is required. If there are number of the quality of service parameters are different, then you require the remarking at the boundary of the second network. So the marking is valid only within the boundary or the administrative boundary of the one network. So you need to find out a mapping between the first level marking, the marking done at the first level to the second level when it crosses another network.